Hello, I would like to welcome you to our presentation about near field communication antennas. We are group number B12. Here are our group numbers. Let us begin.
What is NFC? NFC stands for Near Field Communication. It is steadily becoming a more prevalent form of wireless communication between devices. NFC offers two different types of communication. The first form is a two-way transfer. This form would mostly be used for data or file transfers between devices. The second form is a one-way transfer. This form would mostly be used for verification or authentication purposes between a device and an NFC reader. The basic structure of an NFC device. The overall structure of an NFC device is an NFC chip surrounded by an inductor antenna, or basically a loop antenna. The NFC chip contains the main part of the NFC. The chip contains the data that is sent or received and can be programmed for a variety of uses, while the antenna induces the current which powers the chip. The antenna is generally made out of aluminum or copper, but can be made out of various specialized materials depending on the purpose. These tags fall into two different categories. First category is an E-type, which consists of a loop antenna attached to a chip. A second device is a PBC type, which is the chip attached to a printed circuit board loop antenna.
An NFC antenna is essentially a solenoidal coil. In the lower left is a generic coil, while on the right is a flat coil, shown on a smartphone. The coil must generate a magnetic field within the loop. The surface area of this antenna must fit on the device while maximizing its field. This is done by incorporating into the battery or the battery cover. This field will wirelessly induce a current in any receiving device, which can be then read as data.
Basic transmission. As the picture shows, there is a polling device, which is an initiator, and a listening device, the target. The polling device generates a magnetic field which induces a current in the antenna of the listening device, the NFC tag, which then powers the NFC chip. The listening device itself will then generate its own magnetic field, which will allow for two-way communication, a key property of NFC tags. The magnetic field is therefore used to couple these two devices. The typical operating frequency is 13.56 MHz, with a bit rate of 106 kbits per second. There are three main operating modes: a card emulation mode, passive mode, a peer-to-peer mode, and a reader-writer mode. Passive mode is where the NFC device behaves like an existing contactless card. Peer-to-peer mode is where the two NFC devices exchange information. And reader-writer mode reads or writes to a passive RFID tag.
Other comparable forms of wireless communication. Bluetooth. Bluetooth operates at a higher frequency of 2.4 GHz to 2.485 GHz. Bluetooth also has a higher power consumption and faster data rate of 1 to 4 megabytes a second. Security is that both devices must accept an encrypted key. Wi-Fi. Wi-Fi operates at a higher frequency than both Bluetooth and NFC at 2.4 GHz or 5 GHz. The power consumption is also greater than both NFC and Bluetooth, but data rates of up to 300 megabytes a second. Security of a Wi-Fi device is encrypted through WEP or WPA.
RFID versus NFC. RFID and NFC are really similar. NFC is a newer technology and a more finely honed version of RFID. RFID stands for radio frequency identification. It contains an antenna and a memory chip to store data. RFID tags are extremely tiny. The image below compares an RFID chip to a grain of rice. RFID is mainly used for identification, as it works well at distances of many feet. The chart to the right compares RFID to NFC. RFID has an operating frequency of 13.56 MHz, whereas NFC has the same. Communication for the RFID chip is one-way, whereas NFC is two-way communication. The standards for RFID are ISO 14443, 15693, and 18000, whereas NFC is only ISO 14443. The scan distance for RFID is up to 1 meter, whereas for NFC it's up to 10 centimeters. The RFID chip can scan tags simultaneously, whereas the NFC tag cannot.
Well, as mentioned earlier, there are peer-to-peer technologies such as Android or Something Beam, where you can share a file or contact by touching together two smartphones. That's kind of cool. More important is the potential for contactless commerce. If you think about a payment card such as the London Oyster card, then imagine using your phone for this purpose via NFC. You can see the benefit. Or how about using your smartphone instead your contactless Visa debit card? You could truly dispense with your wallet.
With so many different uses for NFC antenna chips, here are some recent applications. Asus recently designed a computer that can be activated through use of an NFC chip pre-programmed with the access key. Samsung's Nexus phone is also a huge activist for the NFC antenna chip, having incorporated the antenna since the first model. Another interesting application is the Sony Alpha Camera series that has an embedded NFC chip that can be used on selected printers and devices to transfer photos real time. The biggest advancement for the NFC antenna is definitely signing the deal to become incorporated in Octopus cards, which is the all-in-one debit, Presto, and Access card commonly used throughout Hong Kong.
Future. Consumer adoption is still at an early stage. The average consumer does not have enough incentive to start using NFC. Smartphones are popular, but not universal, such as in lesser developed countries. Another obstacle is that debit and credit payment systems are still heavily used by businesses and consumers. Additionally, NFC can potentially play a role in the anticipated Internet of Things. This is a concept of a network of physical objects and people connected wirelessly. For example, NFC-enabled objects like smart meters could provide data easily through contact. There will be no need for entering PINs or passwords as with debit cards. NFC will make data sharing, identification, and establishing other connections faster and simpler. Security concerns must be addressed before people can feel confident in daily use. NFC is at risk from eavesdropping, data corruption, data modification, and data insertion. These attacks are difficult but possible given the right equipment. Active eavesdropping can be done up to 10 meters, while passive eavesdropping can occur up to 1 meter. This is a huge concern for security and must be solved before NFC can compete with other payment systems.
Our next steps. So far, we have covered the most commonly used NFC loop antenna structures and applications. These designs have many promising advantages. However, there are also huge limiting factors. We believe that by designing an NFC chip that operates at a closer proximity and a higher frequency, we will be able to achieve a new loop antenna that is more efficient while reducing the amount of unwanted signal scattering. Through our research, we will test different square loop antennas at a frequency of up to 20% higher than the conventional 13.56 MHz. We will also vary the input power and minimize operating distances to find a square loop antenna that is small in size but optimizes data transfer rates and uses less energy to operate. With these tests, we hope we will be able to formulate a design that, when compared to the commonly used loop antennas, is highly efficient at transferring data while keeping the information safe. We would like to give a special acknowledgement and special thanks to our professor, Dr. M. Bacher, plus OpenEMS, the software that made the project more interesting.